Good afternoon, and welcome to Hand-Wavy Chemistry. There is a famous saying attributed to Paracelsus, which goes, "The dose makes the poison." This idea helps to explain how it is possible for chemists to work with hazardous and dangerous materials safely. For example, during my PhD, I carried out reactions that used substantial quantities of sodium cyanide. We're talking about 100 times the lethal dose. But clearly, I'm still here because we took precautions. Firstly, sodium cyanide is a solid, and solids tend to, for the most part, stay where you put them. So we only handled it in a fume hood. The jar was opened in the fume hood. The balance used to weigh out the material was in the fume hood. All of the glassware that was required for the reaction was in the fume hood. And also in that fume hood was a bucket of bleach. Sodium cyanide reacts with a basic dilute bleach solution to eventually form sodium chloride, carbon dioxide, nitrogen, and water. Every single piece of glassware, the weighing dishes, the spatula, was placed into the bleach solution. Even the atmosphere from the reaction vessel was bubbled through a bleach solution before being exhausted by the fume hood. And of course, I was wearing 2 pairs of gloves, which, at the end of the experiment, I removed and put into the bleach bucket. So in this manner, the risk of exposure was kept low. But our precautions didn't stop there. We also put signs in the window of the lab alerting others to the use of sodium cyanide. And someone was always in the lab with me, observing when I was measuring and handling the material. And had an exposure occurred, we had amyl nitrite on hand to be used while waiting for professional medical attention. So in order to work safely, first, we minimized the risk of exposure, and secondly, we planned for what we would do should an exposure occur. Now let me tell you a different story. In 1996, Dr. Karen Wetterhan was investigating the manner in which mercury ions disrupt the DNA repair proteins, and she had a sample of dimethylmercury. At this time, dimethylmercury was used as the internal reference standard for mercury NMR. During the course of her experiment, she recalls several drops of dimethylmercury falling onto her latex gloves. She proceeded to clean up her work area and then removed the gloves. Unfortunately, dimethylmercury can rapidly penetrate latex and the human skin. Testing samples of her hair in the weeks following the exposure revealed that she did indeed have mercury poisoning. And despite an aggressive course of chelation therapy, about 10 months after the incident, she died. What makes this even more tragic is that Dr. Wetterhan was following the established safety guidelines in use at the time. So while it is easy to look back and say not enough was done to prevent an exposure, nor was there adequate planning for what should be done post-exposure, it is unfair to blame Dr. Wetterhan for these events. As a result of this incident, glove compatibility charts have become widely produced and circulated. And we have started to change the way that we think about PPE. Rather than thinking that our gloves and other protective equipment shield us from the chemicals, instead we think about them providing us with time. If a chemical spills onto a pair of gloves and they are removed before it is able to penetrate, then no exposure has occurred. Finally, The rise in popularity of green chemistry has really started to highlight the need to consider the safety of the chemicals we use and what alternatives could exist. For example, both potassium permanganate and osmium tetroxide are powerful oxidizing agents used in organic synthesis. However, osmium tetroxide is also toxic and can cause blindness. So unless you really need it for some particular case, the potassium permanganate route should be utilized. In a similar manner, many chromium complexes are now being avoided due to the carcinogenic nature of hexavalent chromium. And these safety considerations even extend out to the solvents we use for our reactions, with carbon tetrachloride having recently been banned due to posing an unnecessary risk to human health. So how do we pick our alternatives? And what are the other principles of green chemistry? Well, that is a story for another time. I hope you have enjoyed this video. And if you have, please make sure to like, subscribe, and share it with your friends. And if there is a topic you'd like to see covered in a future video, please put it down in the comment section below. Thank you, and I hope you have a wonderful rest of your day.